Welcome everybody, and today we'll talk a little bit about probability theory. Fundamentally, probability theory is about dealing with and analyzing random events and random phenomena. And it's a theory that's been around since a long time, since the 1600s. And mathematicians like Laplace, Bernoulli, Fermat, Pascal have studied it. But it was only until about 1930 that a rigorous theory of probability was formulated. It's also called the measure theoretic probability. And well, the natural question is why? People have been computing probability since 300 years ago. Why all of a sudden the need to create this rigorous framework? Well, the problem is that before this theory was formulated, people were running into contradictions and paradoxes, and I will demonstrate to you one of these paradoxes. It's called Bertrand's paradox. Bertrand's paradox, and it goes like this. First of all, we consider a circle. Let's say of unit radius, and we inscribe an equilateral triangle in the circle. And it's not difficult to see that the length of the equilateral length of the side of the equilateral triangle will be square root of 3 units. And the question is that what is the probability? So what is the probability that a random chord is longer than this side, which is, say, longer than square root of 3 units. Just if you draw out just a random chord, this looks like a diameter, but what is the probability that this length is greater than square root of 3? Or it could be just another chord like this or like this. So that's what we're interested in. So let's try to solve this. So let's do the following. Let's draw our circle. So let's do this. So let's draw our circle, and let's just draw a random chord. And what I'll do is I'll fix one of the ends of the chord. And it doesn't matter, by the way, that the end that I'm fixing is on top of the circle. Because it's symmetric, rotationally symmetric, this point can be anywhere and it wouldn't matter. Right, so, and consider the tangent to the circle going through this point. Let's say it's horizontal. And now let's draw our equilateral triangle. Let's say look something like this. Right. So this angle then, maybe we'll do a different color. This angle then would be 30 degrees, or not 30, 60 degrees. This angle would be 60 degrees, and this angle would be 60. Consider this angle made by this pink, this our random chord. Let's call this theta. Now it's easy to see that if theta lies between 60 degrees and 120 degrees, then the length of the chord is greater than square root of 3 units, right? So if we have a chord that goes like this, then obviously the length of this is greater than square root of 3. But if our chord is something like, I don't know, like this, then the length of this chord is less than square root of 3, right? So if this angle is uniformly distributed, then the required probability, let's say P, is just 60 degrees over 180 degrees, which is 1 over 3, right? It's a perfectly reasonable argument. But now let's look at it slightly differently. Now, instead of fixing one end of the chord, let's fix the direction of the chord. Right, so let's draw our circle again. And let's draw a random chord, and this time let's construct the equilateral triangle such that one of the sides is parallel to this. So it doesn't matter that this was the particular chord, it could have been any other. So this, and we'll consider this radius here, or this line segment, such that this is perpendicular, and we know that this length will be equal to this length, and similarly this length will be equal to this length. Now you see that if a chord, now let me draw another chord. So if a chord has its midpoint on this, on this part of the radius, then we see that the length of the chord is less than square root of 3, right? Remember this length is square root of 3. So if the midpoint of the chord lies anywhere over here, then the length of the chord is less than square root of 3. And if the midpoint of the chord lies anywhere here, then the length of the chord is more than square root of 3 units. And it can also be shown that this length is actually half, and this length is actually half. Just some simple geometry, you can show that. And so if the chord is uniformly distributed along this line, then, well, half of the time it'll be less than square root of 3, and half of the time it'll be more than square root of 3, because this length is equal to that length. So now we see that the probability is just 1/2. So it's the same problem, but we look at it slightly differently and we get completely different answers. And we're not leaving out any chord. It's not like I'm making a computational mistake here. These are perfectly valid arguments. The problem, though, is that when I say, so this is the problem. When I say a random chord, I'm not being precise enough, right? So you have to specify exactly what random means, and that brings in the idea of measure theoretic probability. This is why this theory was needed, to sort of make precise our notion of a random chord. It sounds fine, it's just a random chord, but mathematically they mean completely different things when you look at them slightly differently, right? So that's why measure theoretic probability was formulated, and so the fundamental object, so measure theoretic probability, and the fundamental object in measure theoretic probability is what is called the probability space. Probability space, right? And we'll talk about this today. Probability space is, well, it's an abstract space. It has 3 components, so we'll talk about them one by one. So let's look at the first component of the probability space. It has 3 components. So the first component is called the sample space, and it's usually denoted by the Greek letter omega. Now, as a lot of you maybe know, the sample space is when you do a random experiment, you get a particular outcome, and sample space is just the set of all possible outcomes. Of a random experiment. Right? So let's say you're tossing a coin and you're interested in the face of the coin, then your sample space would be h comma t, just heads and tails. But omega depends on what you're interested in. For example, if I toss a coin and if I'm interested in let's say the height that the coin goes above ground, right, then omega will no longer be h and t, then omega will be maybe the set of positive real numbers, right? So it depends on what you're interested in. And if you toss a coin twice, then maybe your sample space will be HH, HT, TH, TT, right? So simple enough. And that's it. That's the first element of our probability space. Now, number two, let's go over to number two. We will define what's called an event. Right? An event is a subset of your sample space omega, right, to which we will later assign probabilities. I'll talk about what, precisely what probability means later, but for now, just go with the intuitive idea. So an event is just a subset of omega to which we want to assign probabilities. So as an example, let's say this is our space omega, and maybe omega is 1, 2, 3, 4, 5, 6. Right? Maybe you're tossing a die, and you're interested in the face of the die. And so then what would omega would look maybe something like this. This would be 1, 2, 3, 5, 6. Right, so these are different outcomes. And let's say an example of an event could be, let's define an event B, which is 2, 3, 5, for example. Right? And you can write this as the event of getting a prime number. Right? And you can define maybe another event. Let's call it C. Let's say it's 1, 3, 5, and it's the event of getting an odd number. And you could even define something like, 1, 2, 3, 6. Even though you can't maybe write it in English, but it's still a perfectly valid event because it's a subset of omega. And if you take a bunch of these events that you're interested in, so you want to assign probabilities to A, B, and C. If you take a bunch of these events and you put them in a set, so let's call this bigger set F. So you take the events of interest. So let's say 2, 3, 5, and then 1, 3, 5, maybe 1, 2, 3, 6, and a bunch of other sets. Maybe you're interested in more sets. Then this F is what is called an event space. It's a collection of events that you're interested in to which you want to assign probabilities. Simple enough. And yeah, this is called the event space, and this is, well, there's a little bit more to be said about this. We'll come back to this later, but this is the second element of our probability space. One of the three components is the second one. Right? And we'll talk a little bit more about it as we go along. But before that, we should talk about the third element of the probability space, which is probability itself, or what's also called probability measure. Right? And before we actually define what probability measure is, let's talk about what measure is in mathematics. Right? Let's take a very short detour and we'll talk about what measure is. Well, I mean, there's a whole theory associated with it. It's called measure theory, but I'm obviously not going to go into all of that. I'm just going to give you a very short, friendly introduction. Well, a measure in mathematics is a generalization of the notion of length, of area, of mass, etc. So it's a generalization of length, area, mass, even angle, anything that can be measured. So, mathematicians like to abstract things out, and measure is just an abstract form of anything that you can measure, which is why it's called a measure. And the point that I want to make is that probability is a measure, right? So probability is just sort of a generalization of these notions, which, we have some idea of how these quantities behave. We have some intuitive notion of how mass should behave, how length should behave, what shouldn't happen with mass, what shouldn't happen with length, and things like that. So the point is that probability is a measure. So if we were mathematicians, let's see how we would define a measure, right? So if we were mathematicians, how would you define measure? Okay, let's think about this. So let's see. Definition. A measure is usually denoted by the Greek letter mu. So what does a measure do? Well, as we said earlier in the previous page, we said that these are the subsets of omegas to which we want to assign probability, to which we want to assign measure, in other words, right? So what a measure does is it takes as input these sets, right? The sets that you're interested in, it takes as input that, which is to say, omega, or not omega, sorry, f, takes as input a set belonging to f, and it gives out a number between 0 and infinity, right? And infinity is included because if you want to talk about, let's say, the length of the real line, then it has to be infinite, so infinity is included here. So it takes any set that you're interested in and it assigns to it a number. It assigns to it a measure, right? And what would we want for a measure to, well, what properties do we want in a measure? Well, first of all, maybe I want to say that the measure of the empty set should be 0, right? I mean, let's think of mass. More particularly, let's think of mass. Well, I want the mass of, the empty set, I want the mass of nothing to be 0. And maybe the other thing you want, so let's say we have our omega here, right? And let's say I have a bunch of these little disjoint sets, right, floating around. So let's say I know the mass of each of these little chunks, each of these sets. So maybe when I put together all of these masses, when I take the union of them, which is to say when I put them together, maybe I want the total measure of this to be equal to the sum of the individual measures, right? That's what I want. If I know the masses of these little things, and when I put them together, I want the mass to be equal to, well, the sum of the little individual masses. So maybe the second thing I want is if I have, let's say, A1, A2, that belong to, our set of interest, then maybe I want the measure of the union of all of them, so I goes from 1 to infinity, to be equal to the sum of these individual sets. And by the way, I want all of these sets to be disjoint, right? So I mean, AI intersection AJ has to be the null set for any I not equal to j. So only when they're disjoint can I demand this. And that's it. This is the definition of measure. If you go to a measure theory class, this is how they define a measure. And it's a completely reasonable definition. If you just visualize a measure as mass, then, or even length, area, it doesn't matter, then we would want these two properties to hold, right? So that's what a measure is. Now, when I define a measure in this way, then this mu is any old measure, right? It's not any specific measure. These two properties are satisfied by all of these. But one important point is that if I demand that the measure of my whole set, of the universal set, be 1, like if I demand this, then mu is called the probability measure. Right? So probability is just a measure, except we demand one additional thing, that the measure of the universal set, or measure of the sample space, be equal to 1. Right? And then we write mu as this sort of double p. And this is how we define the probability measure. Right? So if we were to define the probability measure, what would it look like? So definition. So what does probability do? Well, probability takes as input our sets of interest. So if you remember, f was just a set of the events we're interested in, 1, 3, 5, 2, 3, 5, a bunch of other sets. So P takes as input any set in this set and gives out a number between 0 and 1. Right? And what do we want for P to satisfy? Well, I mean, at the very least, P should satisfy the condition that we imposed for measures in general. So the first thing I want is for probability of the empty set to be 0. Right? The measure of the empty set has to be 0. And the second thing I'd want is the measure of the union of disjoint sets be equal to the sum sum of the individual measures. Right? If AI are disjoint. Right? It's very convenient to visualize probability as just mass, and a lot of you may have heard the term probability mass. It's not a coincidence. It's just very convenient to visualize it as that. So, the mass of the little things, when I put them together, they must be equal to the sum of the little masses. And finally, the all-important condition that makes this measure a probability measure is that probability of the sample space should be equal to 1. Right? So, and these three, if you've taken a course in probability, you'll recognize these three as the axioms of probability. Right? They're also called Kolmogorov's axioms of probability, and usually they're just sort of handed out. What I try to do is kind of motivate, why these definitions are the way they are, why these axioms are the way they are. Right? So this is the definition of the probability measure. Now, I said earlier that our friend f, we're going to come back to that. There's a little bit more we can say about this. So, this is what f is. F is the set of events that we're interested in, that we want to assign measure to, right? So let's see what we can say about f and what we can't say about f, right? So let's get back to f. And let's see what we can say about f. Well, let's actually draw out our sample space first. Now remember that the elements of f are, each element in f is assigned a probability measure, right? So first of all, maybe I have to be able to talk about the measure of the complete sample space, right? Because that's the point that makes it the probability measure, is that I've assigned a measure to omega which is equal to 1. Right? So omega must be one of your sets of interest. You must be interested in omega, because if you can't talk about the mass of omega, then, well, there's no point in doing probability, because you have to allow the measure of omega to be equal to 1. So omega, we must be able to talk about the mass of omega, which is to say that omega must belong to F. So when I wrote, this example here, one of these sets must be omega, and this must be included. Maybe the other thing I can say is, let's say I can talk about the mass of any subset A, right? So you're interested in this subset A, let's say. Yeah, let's call it A. Well, if I can talk about the mass of this subset A, then whenever I take it out and whatever remains, I have to be able to talk about the mass of the remaining thing as well, right? Intuitively we want that to happen. If I can talk about the mass of this, and I can talk about the mass of the complete omega, then I have to be able to talk about the mass of whatever remains. So whatever remains is actually a complement. So if A belongs to F, which is to say that I'm interested in the event A, then it must be the case that a complement also belongs to F, right? And finally, again, let's draw another picture maybe. And let's say I have a bunch of sets again. This time it doesn't have to be disjoint. Let's say I have a bunch of sets here. Now, if I can talk about the masses of these, little blobs, then when I put them together, I still have to be able to talk about the mass of them, when I put them together, right? So what I mean to say is, if A1, A2, all the way is in F, which is to say that I'm interested in all of these little events, then when I put them together, which is to say that union of all of them must also belong to F. I have to be able to talk about the mass of the whole thing put together as well, right? So demanding these three conditions is actually completely reasonable, right? And when F satisfies these, completely reasonable restrictions, then F is called a sigma algebra over omega. Right? The sigma algebra over omega. Usually the conditions of sigma algebra is just handed out to you. Again, tried to kind of motivate why the three conditions are the way they are. Right? So we've motivated the definition of the probability measure. We've motivated the definition of F. And so the probability space then, the probability space is, well, simply when you put together the three elements that we just discussed, the omega, the F, and the measure P, right? So what is omega? Omega is the sample space. What is F? F is the sigma algebra over omega, and P is the probability measure. Well, when you put these three things together, then this sort of abstract space is called the probability space. And to sort of give an example, kind of a real life example of what a probability space looks like, let's take a very simple omega being, 1, 2, 3, 4, 5, 6, right? And let's say my F, my events of interest are, well, omega has to be there. And, well, actually, let me bring this here. Well, omega had to be there. Well, if omega is in F, then omega complement also has to be in F. So what's omega complement? It's just the empty set. The complement of the universal set is the empty set. So phi has to be there. And let's say I'm interested in the event of getting prime numbers, right? So like this. And if this is there, if this is present in F, then the complement of this should also be present. So 1, 4, 6. Right? And anything else? Well, no. This is a complete, because if you take the union of these, so for example, I said that union of any of these events should also belong to F, but when you take the union of these two, that just becomes omega, so it doesn't matter. So F is, this is my sigma algebra. And my probability measure, let's define it the following way. Probability measure of the event 2, 3, 5, let's say it's half, and maybe the probability of 1, 4, or 6 is maybe half. So this is how the probability measure is defined. And so this is my sample space. This is my sigma algebra, and this is my probability measure. And when you put all of these three together, then this is called the probability space. Now, the precise reason as to why the paradox that I talked about, the Bertrand paradox, what exactly is going on there, that will take a little bit more discussion. Maybe we'll discuss that in the future at some point. But this is a very simple example of what a probability space is and what is required to not fall into this sort of pitfall of contradictions and paradoxes. So if you have completely defined your sample space, if you've completely defined your sigma algebra, and you've completely defined your probability measure, then you're ready to take on any problem in probability theory. And that's the point of the measured theoretic probability. So yeah, thank you guys for watching, and I'll see you in the next one. Goodbye.